Hi everyone, we are Group 14, and I'm going to introduce our mechanic clock and tell the reason that we choose the pendulum clock as our topic. Speaking of the clock, it used to just appear in monetary until European scientists took them as the tool which could help them measure time precisely. Due to the poor mechanical device at that time, they usually use the natural energy like water or sun instead of electricity. So they need a device called a schema to transform the energy, like liquid-driven schema. It could transform the water energy, kinetic energy of water to the mechanical energy. And what we use in our pendulum clock is called grasshopper schema. It could save a lot of energy and the structure is simple too. And there is two key factors in a schema. Its accuracy and reliability. Reliability of a schema depends on the quality of workmanship and the level of maintenance given. A poorly constructed or poorly maintained schema will cause problems. The schema must accu- The schema must accurately confer the acceleration of the pendulum. The schema must accurately confer the acceleration of the pendulum or balance wheel into rotation or of the clock or watch gear chain, and it must deliver enough energy to the pendulum or balance wheel to maintain its acceleration. And this is also the advantage of grasshopper schema. And the accuracy depends on the experiments. So we will do some experiment to test our machine.
First, I'm going to introduce the simple harmonic motion, which is known as SHM. The basic definition about SHM is that by analyzing the whole motion, any time we analyze it, the force that affects must be proportional with the current distance with the balance point, which is known as x. The ratio is generally known or write as k. So we get F equals to minus kx. And by merging with the Newton's second law, that F equals to ma equals to m times the second differential of x, and equals to minus kx as the definition. By sorting the equation above, we can get kx plus m times kx double prom equals to 0. And by sorting, we get the easily solved differential equation that x plus m over k x double prom equals to 0. By solving this equation, we get that x of t equals to sine omega t plus cosine omega t. In this case, that omega equals to the square root of k over m. And as math or as physics, we can get that the period t equals to 2 pi times the square root of m over k. Now I'm going to introduce a simple case of the pendulum, which is when the angle of the movement is smaller than 5 degrees. The symbol theta is the angle of the movement, and the m is the mass of the pendulum, and g is the gravitational constant, and L is the length of the pendulum. By analyzing this model, the horizontal force, which is the force that truly affects, is mg sine theta. And the distance from middle is L sine theta. So we can find that this is a simple harmonic motion, which is SHM. By using the formula we just proved, the period equals to 2 pi times the square root of L over G. But we can analyze it with a different angle by analyzing the equation of the motion, that ml theta double prom equals to minus mg sine theta equals to minus mg theta in this case. By sorting it, we can get the differential equation that we just proved when we proved the formula of simple harmonic motion. By experience, the period t equals to 2 pi times L times the square root of L over G. But in general case, which is theta might not be smaller than 5 degrees. We need to use more force to know the precise period of the motion. As we got m times omega squared times L equals to 2g cosine theta 0, which is the max angle of the movement, minus cosine theta. The theta is the current angle of this position. By getting omega reciprocal, which is dt d theta. As a tool to get the period we want, omega's reciprocal is the square root of L divided by 2g cosine theta 0 minus cosine theta. Then we can integral it, so we can get the period equals to 4 times the square root of L over 2g times the integral from 0 to theta 0 of 1 divided by the square root of cosine theta 0 minus cosine theta d theta. The reason that it times 4 is that the motion is from the balance point, which is when theta is 0, to the max point, that when the theta is theta 0, then back to the balance point, then go to the max angle again, then back to the balance point again. So we can know that it's the 4 times of when the balance point to the max angle, which is integral from 0 to theta 0. As we can see, it equals to 4 times the square root of L over 2g times the function of theta 0. And the function is ugly, but we can guess that it is an increased function as the integral above. By this formula, we can know that even though the theta is bigger than 5 degrees, the whole motion is still periodic, and the length of the pendulum still has the similar effect on this motion. But further, we can know that if we want the period to be longer, we can try to let the angle become bigger because it's still periodic.
Hi, I'm Bo Junfeng, and this is the simulation part. Before I show the animation, I want to talk something about simple pendulum. We all know that simple pendulum has periodicity and isochronism, which can be used to measure time. However, there is a resistance in real life. I can show you the animation with a resistance. This is the original height of the pendulum. You can see the air resistance keeps slowing down the pendulum, and the height becomes lower and lower. As time goes by, the pendulum will totally stop. I think that the clock that can only work for a few seconds is not useful at all. Therefore, we found a way to make this pendulum keep moving and almost non-stop. Let me show you the animation. We add some devices to the original pendulum. Here is weight, which makes the blue and large gear rotate counterclockwise, and then the small gear will always try to rotate clockwise. Nevertheless, this rod prevents this gear from rotating, so the device on the pendulum will heat it up and make the rate
gear rotate, then the teeth will hit the device on the pendulum. Then the pendulum will back to the same height as previously. You can see that again. It may push this device and it will go back. To simply put, we use the gravitational rotation energy of the weight to counter the work generated by air resistance. So the pendulum will keep moving and non-stop. And it may be able to measure time more precisely than the original one. There is the simulation part.
For the practical realization, we build a simple pendulum clock, test its ability of measuring the time, find the error and the probable reason. We measure the time of 60 swings and find out the average time will be 27.2 seconds, but the theoretical period of time is 0.58 seconds, since the length of our pendulum is 8.5 centimeters. So the theoretical time of 60 swings will be 34.8 seconds, which is much more than the actual one. We think the cause of the error is imprecise measurement of the center of gravity due to the unevenly density of the stick and attachment. We also find out from the recorded videos that every swing movement of the pendulum is not complete, so the actual time of a swing period will be less than the theoretical one. However, the period of every swing is approximately the same. Therefore, the pendulum clock can still be used to measure the length of time, with accuracy of about half a second.